And most of my research involves ways to use convection-allowing ensembles to predict convective hazards, so tornadoes, straight-line winds, large hail. And so using convection-allowing ensembles, which have just basically come on the scene in the last decade, has given us an opportunity to try to come up with new ways to visualize this information, and which I'll talk about throughout this talk, I think is really critical to using these ensemble systems effectively. So if you want to download this repository, git clone, there's the address there. I think it's probably the smallest repository of anyone. I believe it's a README and one HTML file. So everything I'm going to be doing is going to be based on that. It's a pretty simple example. And so we'll be going through, especially during the second half of the talk, looking at how to use some web-based technologies, so HTML, CSS, and a package called D3 together to visualize data sets within a web browser. And so once we get to that point, you can just open your favorite web browser, Chrome, Safari, hopefully not Internet Explorer. Things often break in IE, at least early versions. And then open that one file once we get to that point. So I wanted to open just with kind of a general question of what makes for effective web-based forecast visualizations. So everyone probably goes to some website to see what, say, the NAM or the GFS is showing in terms of forecasts, maybe some convection-allowing models. Pivotal Weather, the COD site, a variety exist. And so I kind of just want you to think a little bit about, for the first part of this talk, what are the aspects of those sites that you like? And why do you go to the sites you do to get weather information on the web? Here's a variety of examples of ways to visualize ensemble information. And so now that we have ensembles, the design choices that we make in terms of graphics and interactive tools are even more important because there's so much information there. And so it's a lot easier when you have an ensemble to make something that maybe isn't as effective in terms of conveying the information, because there's now this new additional dimension of the data that you have to consider. And so here's just a handful of examples here that I pulled from the web in terms of you can have plumes, and I think Tyler will be talking a little bit more about specific products this afternoon. But you have different ways in terms of probabilities, box plots, and line charts, different ensemble soundings methods. And so these are all sort of types of products that you have to think about how to design and what types of information to get across. So more generally, if you have a lot of complex information, there's certainly many ways you can visualize it, and I'm going to show a couple of examples of bad visualizations to start, which aren't actually in the weather sphere. So here's one. This chart here attempts to describe the new healthcare system. This was initially designed to actually emphasize the dysfunction in terms of the bureaucracy of the system. But obviously, there's various different elements here that are thrown together in this plot. You have different colors, you have different shapes, you have the position and placement of these objects, you have a legend at the bottom that would take hours to describe everything on this plot. So obviously, this is not an effective visualization. And some of what we see with visualizations are sort of this intuitive nature to them, and it's hard to put into words exactly why something, and you might see this when you go to different websites. You can't necessarily specifically pinpoint why you like a certain visualization or a certain website in terms of their graphical presentation, but sometimes it just goes back to being intuitive, easy to understand, not a lot of cognitive load in terms of trying to make sense of the information. So this is obviously not a great visualization, so we'll give this one facepalm. Okay, so here's another visualization, same type of strategy, not the greatest way to sort of present a lot of complex different models. I see this a lot of time in different talks from NOAA's operational model suite. Again, the point is to emphasize the complexity, but still, there's lots of different elements here, and you could probably put together a fairly effective visualization for this, even with the complexity that exists in NOAA's operational numerical guidance suite, but presented as is, it's not the greatest use of, not the greatest way to present this information. So this is a double facepalm. Okay, so getting back to convection allowing models and ensemble information, when I started some of this work back about a decade ago, we were looking at some of the early ensembles and convection allowing models. And so here's a web page that I developed with a couple of folks at the National Severe Storms Lab in Norman, Oklahoma. And the objective here was just to present different forecasts that exist side by side so you can get a quick and dirty glance at what the forecasts are showing, and then you could also present observations within the same framework and have a way to not only look at the forecast, but to verify the forecast. So this was 2009. This was an example of the super derecho that occurred in Kansas, Oklahoma, Missouri around that time, showing some of the forecasts. This is just when I started to think about some of these ideas. And then in the past couple years, I've been part of a project called the NCAR Ensemble. And so here's a screenshot of the last forecast from the NCAR Ensemble system. And so some of these design elements actually that went into this early web page back in the 2008-2009 period, almost a decade ago, I took and sort of fine-tuned, got rid of some of the menus and cleaned it up a bit, and then developed a Python-based package to actually produce the graphics. So again, Tyler this afternoon will talk a little bit more about Python in terms of creating effective ensemble visualizations. I'm mostly going to focus on kind of the front-end web-based aspects of this system. And so we got a lot of positive feedback for this website from forecasters, from the private sector, from just users interested in convection allowing ensemble information. And so we've learned a lot about not only the science behind how to design ensembles, but how to visualize them in this project. So basically, there's sort of a paradigm that exists on the web today, and it's this paradigm of predominantly consisting of static images. And so this is an example here where we just have some rollovers at the top to toggle between forecast hours just below the menu bar, and then we have our graphic there that's presenting some ensemble information and showing departures from climatology. So how this works, you generally retrieve some model data or produce some model data, say if you're running WRF simulations, and then pick some visualization software like NCL or Python, Genpack to produce imagery from that model data. You push all those images to a web server, and then maybe develop some sort of website to interact with those images. And so here's an example here. You're on a laptop, you're on a computer, you make a request via your web browser, and the web browser's making HTTP requests under the hood, one of them being the GET command, and so that's telling the web server to send it an image, and it could be sending it many, many images, depending on how many images are on a web page, and those are sent to the browser. And so in this paradigm, there's a limited amount of interaction with the data. You're confined to the graphics that were already generated and the visualization approach that the developer took to, say, loop through them if you're doing loops, or, say, rolling over links. And this paradigm is sort of referred to as a synchronous request paradigm, where one request is made to the server, the images come back to the browser and are displayed, and that happens and it results in a complete reload of the web page. And so a lot of what I'm going to talk about today is looking at a different sort of paradigm, an asynchronous paradigm where you're actually requesting data under the hood and you're not involving a complete reload of the web page to interact with the data. So some web-based visualization packages that exist, many exist, and they've been exploding in the last 5 years. Some are more higher level than others. So some exist like Google Charts. There's a few other examples there. And most of these libraries use JavaScript to produce web-based visualizations. And over the last 5 to 10 years, the browser processing of JavaScript has improved dramatically. JavaScript is used extensively across the web. on both the client and server side. So just some background, JavaScript is largely a client-side scripting language, so the web server sends the browser a bunch of JavaScript, and then that's rendered via the JavaScript engine in the browser. Whereas PHP is, say, a server-side language, where all that's rendered on the server side, and then what's sent to the browser is largely HTML. And so some of these new web-based visualization packages, which I'll talk about a little bit more about here over the next couple slides, use JavaScript and provide frameworks to interact with the underlying JavaScript. So say 12, 13 years ago, the early versions of Gmail, Google Maps, were really among the first to use these JavaScript libraries to produce what's basically a web application. And so if you're in JavaScript or in Gmail or on Facebook, the page isn't loading, the entire web page isn't loading repeatedly. It's under the hood constantly requesting data from the server in an asynchronous manner and reloading or changing elements of the page one at a time, depending on the user interaction. So a lot of this under the hood uses what's called XML HTTP request, or just XHR. So this is a technology that was put into the JavaScript standard a while ago in the early 2000s, and it's a method to transfer data between the browser and the server. So this sort of forms the backbone of what's called AJAX, which is asynchronous JavaScript and XML web development. Really, this is again just some terminology that's associated with the browser having the functionality to repeatedly ping the server, pull back whatever data it needs, say in JSON, CSV, a variety of other formats, and then update elements on the web page as needed. And so there's a lot more, there's responsiveness to it. You're not having to load everything over and over again. It's efficient from a network perspective. You're only sending bits of data that are required based on the user interaction. And like I said, the data is transferred in a variety of different formats. And so this paradigm here is more is an asynchronous process that really allows for an extensive amount of interaction between the user and the browser. And so through the process of developing this website for our NCAR Ensemble system that was an experimental convection allowing Ensemble running from 2015 to 2017, I wanted to create some new visualizations that took advantage of this sort of framework of having asynchronous requests, having the ability to interact with the data sets in a more, in a deeper way to try to come up with ways to really dig into the Ensemble data. Just to show some statistics of the usage of our website, just to make the point that it was pretty heavily utilized over a 3-year period. Just some stats in terms of usage by time of day. Obviously, there's a peak in the early morning hours, so the forecast would run at 0Z overnight, and then you get a peak in the early morning hours with folks getting up and looking at the forecast, and then it would decrease through the day, and then there was a secondary peak late at night, so those were the power users that were staying up late at night waiting for the forecast to come in, say 10, 11 o'clock. Those are mountain time. And so our top 5 network sources, the first couple there are within NOAA and the National Weather Service. So they were big users of this Ensemble system, and we had a lot of feedback from NOAA and the Weather Service. Some of our big dates, Winter Storm Stella in 2017, March 2017, was a huge day. It was a winter storm on the East Coast, and so that got a lot of visitors and page views to the website. A couple other winter storms, an East Coast storm, so you're hitting a lot of the large metro areas, so that's providing a lot of eyeballs onto the website. And then a couple severe weather events, large severe weather events that covered a good chunk of the Central Plains were in the top 5 for website page views. In the bottom there, I have just some stats showing the average session duration on the website. And so this is sort of hovering around 5 minutes. So this is an average. Obviously, there's people who are on there digging through the data and maybe on the website for 30 minutes at a time, looking through a lot of products. But if you just look at the average, it's essentially around 5 to 6 minutes. And so there's really only a subset of products people were looking at when they were on the site, and those mainly had to do with just some of the summary convective products. People wanted just an easily digestible way to say what's happening on a given day, where are the most intense storms in the ensemble, what are the probabilities. And so a lot of our products were tailored to trying to come up with some way to summarize all this information. So I'm going to show a couple examples of this, and I'm going to jump to the web to do so. And so the first tool was basically this plume diagram tool, which is nothing more than just a line chart of the different ensemble member forecasts. So underlaid in the top is 2-meter temperature, and then just some bars showing the interquartile range there and the ensemble mean. And then in the bottom panel, there's hourly QPF. So you can kind of, in the underlay, see the individual members, but also what's more emphasized is just the overall distribution. And then in between, there's indicators for the predominant precipitation type for a given hour and the ensemble mean 10-meter wind speed. So you can quickly see what's going on at an individual site, so this isn't too much different from, say, the SPC Schruff plumes or other ensemble visualization techniques that exist. But the difference here is this page is designed to really be asynchronous and just require data that's transferring back and forth from the server. So there's this map here that can pan and zoom, and you can select different sites in the domain. And this is all built on D3, which I'll talk about during the second half of the presentation. You can pick different sites here. And so when I click on this dot here for Akron, Colorado, the data was retrieved from the server and the lines changed. Let me pull something a little different to make it site further away, to make it more obvious. So what happens here under the hood is the user pans the map, highlights a station, clicks the station, the data is pulled from the server, and the lines are essentially regenerated on the fly. And so none of the other aspects of the web page were reloaded. That was the only thing that changed, was the site changing, and a new data set took the place of the previous data just for a different site. And so this is also taking place by switching different fields here. So in the bottom panel, if we go to a different preset field here, so we're looking at QPF, it looks like it's all rain for this station. So if we hit snow, everything should end up going to 0. So that's the same type of interaction. So this was a pretty basic first attempt at trying to develop something that made use of these technologies. The second application was a SKU-T viewer. So this is a little different in terms of plotting in SKU-T space. But same idea, we have now in the vertical, just 10 members here showing the different ensemble members. And for this, we've retained the rollovers here at the top, and so we can actually go through hour by hour and see the evolution in time of the soundings. And you'll see during the first couple slots there were actual observed soundings which were overlaid to give us some indication of how the ensemble was performing for a given day. So it was good for retrospective analysis. But the same map type capability exists. This was actually restricted to a set of sites, sounding locations over the US. And so you can click a site and it would load the data and then basically update the visualization. Well, the final visualization that we developed is quite a bit more complex. And so I'm going to just briefly talk about this, and I'll hit it at the end after we've talked about D3 a little bit to give us a little more appreciation of this. So I'll pick a forecast here from the past. And so this is the same type of map that I was using before to pick stations, and now I'm plotting basically the locations of storm objects in our forecast for all 10 members in the central part of the plot. I'm actually using the Hagelslag package that David Gagne produced to identify the storms using a watershed technique, and then just plotting the centroids of those locations as dots in the dot size is, I believe, representative of an updraft helicity magnitude associated with that storm. And so here's all the storms within this particular 48-hour forecast. And then in the upper left, there's actually a scatter plot here showing different properties in bulk by forecast hour of all the storms in the domain. And so you can go through and easily pick out where the, say, strongest magnitude updraft helicity storms are on a given day. You can interrogate those storms. You can see which forecast hours they occurred at, both in this visualization in the upper right, but then also the shading here is indicating the number of objects. So if you roll through the hours, you get an indication of where storms were forming at various hours. And then you can look member by member, actually, over the entire forecast to see the individual member depictions of the storms. And so these are both changing in sync, both our scatter plot and the main option here. And we have a variety of fields over here to change that scatter plot on the fly. So we can see just bulk statistics for this forecast of various fields, say updraft helicity and CAPE, and you can just quickly view these, the properties of the storms and a bunch of filters here as well. Also changing colors based on forecast hour duration and member. And so these are all, again, built on this concept of this asynchronous interaction with the server and a package called D3. So let's jump back here. And so these are the examples. Okay, so has anyone used D3 before for any sort of visualization? Okay, so maybe 5, 6 folks. Okay. So just what is D3? So you can see the address there for the website and the GitHub site. It's a JavaScript library for producing interactive data visualizations in web browsers. It makes use of web standards. So it's creating SVG objects within the browser via JavaScript. It uses SVG, HTML, CSS. So to make use of this, browser needs to support SVG, which is basically all modern browsers. I mentioned Internet Explorer. Internet Explorer 9 and prior to that, I believe, didn't support SVG, but all modern browsers these days do. D3 is fairly low level. I'll make some more comments about that later in the talk. But the aspect of it being low level, somewhat closer to the JavaScript the native JavaScript allows for extensive control over the visual elements in the web page. It's interacting with, I'll refer to this as the DOM or the DOM hierarchy, which is the document object model, which makes up a web page and how things are related on a web page. And so other packages exist on top of D3, actually, to make visualizations at a little higher level with less custom control. And so I'm going to go through some examples here for the next 15 to 20 minutes with D3. And so you can follow along with the code that I gave you. So you'll see in the code there's a mix of HTML, some CSS, and a block of JavaScript that does all the heavy lifting. So one of the main ideas here for D3 is to understand selections. And so this is similar to other JavaScript packages such as jQuery. jQuery has a similar type of idea, and it uses these CSS-style selections to identify which DOM elements and nodes to create, manipulate, or delete. So we have, say, a web page that you've written, and you have HTML, and you have these tags, and say there's the paragraph tag within an HTML document that's wrapping some text. And here's an example, and say we want to change all the text color to chartreuse. Here's the code that does that. There's a line, basically D3, and so you see these chained commands. And so that's one of the styles of D3, is you have these chained accessor functions. And so there's D3.selectAll, and so that's going to look through the entire web page and select all the elements that have this paragraph tag and change everything with them using the style function to have a color of chartreuse. Another example here using the selection is, let's say we only want to get the first div element. So this is another HTML element that's used to separate things on a web page. So select is just going to get the first. Select all will get all of the elements on the page. And so we're making use of also classes and IDs. You can put classes associated with a tag that sort of puts an identifier on different HTML elements. and this is via CSS, we can say we want the divs with the class of header. And so that's going to pluck those out and then say, in this example, change the alignment of that div, which is just a wrapper around some block of text, or change the alignment to the center of the page. So this is an even basic example than what I gave you. This is just a very simple framework. You have your HTML and your header and title, and then so it's loading D3. You can see that script source. We're loading D3 from the web. We're actually using V3. There's version 4 and version 5, which are not backward compatible. So if you do use 4 and 5, you have to make some syntax changes. But here, let's just focus on the body here. I've wrapped some text in the paragraph and div tags. And so this is what it looks like with this basically block of text. We'll show up this in the browser, just some text. And then I've added there in the JavaScript block 3 D3 commands, one changing the paragraph to color, one changing the div alignment, and then one actually changing the body tag font size. And so it's going to select that body tag, everything within it. It's going to give the font size of 36. And so that's what ends up resulting with that. So this is sort of a contrived example. If you wanted to do these things, you should do them just purely with CSS. You don't need D3 to use any of this. But the idea of selections is really crucial to D3, because then you can start selecting your SVG objects and changing the properties of those on the fly. Okay, so like I said, it's really the creation and manipulation of these SVG elements that makes D3 really powerful. So often the first step is to basically create, say, a container. This has nothing to do with Docker containers. This is just, say, a generic container for your SVG elements. And so what this piece of code here does that, selects the body. It's going to take that tag and append to the end of that within the code a tag of SVG, an SVG element. And it's going to give it a width and height of those two pixel values. And so that will change your DOM to basically just throw this SVG line in there. That's what the result of that code is at the bottom of the body, since we're appending to it at the very end. So that's the first step in, say, creating one of these visualizations with D3. You can read a lot more about selections with the documentation online. I'm going to jump to some of the good stuff, basically interacting with data and having these data-bound visualizations. So once you have some data that you want to visualize, the data, D3 has been designed so the data is determining the look and feel of each object on the web page. So here's now the example that you have in front of you. And so here's a block within that, a script block that has some arbitrary data. And we're going to use those values in the array to make some rectangles on a web page. So that the next block, what I just showed you, was just creating a container. And then the final block there is where really everything is drawn. So it's going to select all of these elements that have a class of bar, and none of them exist to start with. And there's no objects. You can look at the source code of the page. There's no objects with a class of bar that exists. I'll talk more about that in a second. So it's going to pair the data, that array of data, with these elements, with the selection of all the elements with a class of bar. There's this enter function, which actually produces the elements if they don't exist. And how it produces those, it's going to append rectangles to those with attributes that have a class of bar, have a width that's based on the data. So this is really where the power of D3 comes in here. So you're prescribing the width of our elements based on the data values, the Y locations on the page. You have D, which is representing the data, because it's being passed in here to this attribute function. I is just an index, basically, over the data, so 0, or I believe 0, 1, 2, 3, 4. So sometimes that's useful for, say, creating evenly spaced, say, rectangles on a web page, 1, 2, 3, and you're multiplying their eye by 50 pixels to separate them, and the x position of 10 pixels. And so this data function is binding the data to those elements. And the question here, the first element in that selection is paired with the first data array element, and it's stored in the data property of that element. But as I mentioned before, what if there are more data than selected objects? Say you don't have any objects, but you have this data. And so how do you pair them together? Well, that's where these special enter selections come in, and it's accessed by enter. And they're bound to the new elements through append. So this is what you see when you should see if you open that code, or run that open file, go to the browser, file, then open file. It should basically just draw some number of rectangles. And the height of those, the y value, is determined by the data. And so in that example, so the y values, you're going to have to, you basically subtract the height of your SVG element because it starts at 0 at the top corner. Not the bottom left, actually the top right, that's the 0 pixel. And so to get those oriented in such a way, you have to do that subtraction. And so if you looked at the code in the browser, this is what you'd see. You see the SVG container that we created. So in the example, I think the width and height are slightly different. And then D3 created all these SVG elements with different heights, the same width, and at different x and y positions on the page, with all having this class of bar. So initially, we didn't have any objects. We had this data array in that example, and then it created all of the objects for us. And so this is the general sort of pattern with using D3, this update pattern. And the first thing you usually do is bind the data to the SVG elements using data. And oftentimes, there'll be reasons to use other functions such as exit and enter. So say you have 20 rectangles or 20 lines, 20 ensemble members, or 20 circles on a web page, and you're updating it, and there's only 10 pieces of data. Well, the exit and remove functions will get rid of those elements that aren't associated with this new data that's come into the web page to be plotted. And adding the elements, just as we saw, is accomplished with this enter append construct. And so sometimes you don't need to enter or exit any different data. So if we look at, say, those line charts that I showed you on the web, on the NCAR Ensemble site, there's a fixed number of forecast hour and ensemble members for each of those sites. And so we're not creating new lines. We're basically just binding the data to the existing elements with the .data function, and then applying a transition between those two states. And so D3 has all kinds of transitions built in to transition from one state to the other. So this is sort of just this kind of a summary, this Venn diagram of what's going on. You have your data set, you have the elements that may or may not exist yet, and they are joined via an update. If you have more data than elements on the page that exist, then it will create new ones. And if there's more data or less data than you have elements on the page, it will remove the elements that aren't associated with the data. Okay. So I was just going to quickly go through some of the details of that in the code, and then give you a couple minutes to play around with the change some of the elements in there. So if you see here, okay, I think this shows up fairly well. This is what's in the repository. Let me expand. Okay. So this has a few additional parts to the page, but here's this update pattern right in the middle here. So when you can actually see here I've set up this, I'm selecting this SVG, and I actually set up a click interaction. And so when you click that box, it'll shuffle the data that's been provided in there and replot the rectangles. And so here's the first part. It's selecting all the elements with bar, which let's assume they exist already. So this is after the first time it's drawn. It binds it with data. It removes the rectangles not associated with data, but there's a fixed amount of data. The number's not changing, so this really isn't needed. It's adding new rectangles on click, which this actually isn't needed either, but because the number of data size of that array hasn't changed. And the transition, though, is what's needed. So it's taking all those bars, applying this transition function, a duration in milliseconds, and changing these two elements. So the data, each one of those rectangles, its height is changing because the data associated with that particular element is changing. And the position is changing. So you need to change both of those to update the state. So that's all triggered when you click on that SVG element. Okay, so I'll give you a couple minutes just to maybe try a few things with that. You can change the number of the elements in the array. Say if you add more or remove them, see what happens. You can change the mouse event that triggers the transition. It's now set to click. If you just click mouse down, you'll notice that if you just press your mouse or keypad down, trackpad down, it will trigger it, or mouse up, or mouse over. And you can change, say, other elements via the properties, CSS properties, or even using D3, the rectangle size, the transition time, the size of the element. So try a couple things, see if you can break it. If you have any questions, I can come around and answer those. I'll give you just a couple minutes there. So what you'll notice is the data array. So these are set up to be the pixel values, right? If you wanted to, say, plot something, and I'll briefly show the code to do this. Say you have some array of data that's temperature from an ensemble or a forecast. So you need to basically have a mapping between the temperatures and the pixel values. So everything that's done here, because you're plotting things in a browser, is going to be based on pixels. And so you can create a function that basically just takes in, say, a temperature value, and then outputs an associated pixel value. Here I've simplified it. So those numbers there are associated with a pixel value that is related to the height of each one of those rectangles. But if you took away half of those data, only half the number of rectangles are plotted. So the idea being that D3 really is creating all these objects based on what data is being fed into the web page. Any questions so far? Anything at all? So if you wanted to so this part here is basically the initial part that's being run before there's a click, right? So it's using that initial array. So you're talking about down here with the click using a different array? So, yeah, I mean, you could, that's perfectly fine. I mean, right. So this shuffle basically is creating a new array, right? And so you can have another array there that when you click, it transitions to that new data set. So say you only want to change between, two different arrays. And change back and forth to maybe see the difference between those two. Then in this, the function that's driving the update, when you click the SVG container, then you can just you can get rid of this actually and use data2 down right here. Yeah. Right, exactly, yeah, and
Did the example you said and took out, say, half the elements of the var data, and then you get less bars, but they're about half the
Oh yeah, could you use the mic?
I did the example you said and reduce the elements in the data array, reproduce the HTML, and the bars are half the length but half the window. I wonder if you could work out how to make it dynamic so that no matter how many bars you have, they could use the width of the window. Yeah, that plot.
So you're right. So your width here, so it's fixed. So we know that the width is set to be 1250. So we could basically come up with the length of this. Let's see, I believe it's, who knows JavaScript well? I think that's the length of our array. And then we could do something like bar width equals, well, we're just going to hard code that for now. This work in JavaScript. Let's see. Let me see if this works. You'd have to do something along these lines. You basically can, come up with a way to, and that's the nice thing here. All this can be dynamic, right? So with these accessor functions here, every element of each object that's being created, it can be driven by the data itself. And that's where you use this function, this accessor function. It's passing in for each one of these elements the associated data value. And you can define the height, the width, and everything associated with those SVG objects. Okay. So let's jump back to here. Okay. So like I mentioned, I'm going to highlight a few things that are relevant for dealing with meteorological data sets. One of them being scales. So I had that array that sort of matched what we wanted the heights of the bars to be. If you have some data set that you have, and you have temperature data, you can use a function like this. There's linear scales for continuous fields. There's scales for categorical fields. D3 can do interpolating sort of on the fly in these scales. And this is an example just to map a given value from a domain and return a result in a range. So example, temperature to pixel values. So you have your domain here of, say, temperature in Fahrenheit and the range of values you want those to be associated with. And it will, by calling x, which is now our scale function there, provide it with a temperature, and out will pop a pixel value. And so this is necessary for basically plotting meteorological data sets with D3. And there's also a lot of useful methods for plotting scales. So if you're plotting something like the plume diagrams I showed you, there's lots of functions to, say, plot ticks, tick labels, axes on the scale to make it really easy to do so. So retrieving data, there's functions, say, that work with a variety of formats. An example at the bottom is just CSV. So a lot of the data that is on our NCAR Ensemble website is either in CSV or JSON format, and it's read in by those tools. And so here's a function for CSV. It's going to read in that CSV file. And then after it's read in, it will pass the data from that CSV file that's already been parsed into an array and put it in this data array and then the function that follows, you can basically put all your code to draw the elements once it's been read in and parsed by D3. And what makes these maps so easy to draw are the functions within D3 for plotting on maps. And so there's functions for putting, having this capability of zooming and panning, the idea of having a slippy map so you can pan around a map, and then plotting, say, dots, just coming up with projections, transformations between lat-long coordinates to pixel coordinates, which is really useful. And so that's what's done with this map here. Basically, it's just a long list of station locations of lat-longs, and then that's passed through that a function that I've basically built with, taking advantage of a lot of the D3 built-in functions to convert those to pixel locations in that map. So now you should be able to understand a little bit more about, say, this Ensemble Storm Viewer, which is one of the more complex, the D3 visualizations that we've made to use Ensemble data. Really, all these dots, they're just CSV or CVG circles that are generated. The rollovers at the top are changing the CSS elements, so it's selecting a certain set of elements and hiding or showing those elements as the mouse rolls across the top of the screen. The selections are also used for the colors of each of those boxes associated with the rollovers and the members. We're counting just the number of storms for each ensemble member and shading it appropriately. Same thing with the scatter plot, just setting up a small domain, plotting dots, changing different characters, elements of the dot based on the data, and then changing them via this D3 update method. So if you click on one of the panels, the scatter plot fields, it's going to take the data and dynamically just reposition those dots within that small scatter plot. So I'm going to jump briefly to just some other examples with D3, non-meteorological examples, because this is a really powerful package. So there's this site called blocks, bl.ocks.org. And these are just all examples of different types of web-based visualizations. And this is nothing more than D3, HTML, and CSS. And you can see the code here, and you should have kind of a basic understanding now of how this works. So here it's reading in, say, a JSON file, and then running this block of code to create this visualization, which is some data set, and you can actually dynamically interact with the data set within the browser. So there's no plugins here. This is all SVG and JavaScript in the browser, doing things with D3. So check out a variety of these examples. There's a lot of examples that are relevant to the atmospheric sciences, plotting data on maps. So here's an example. This is all just basically probably a CSV file or TSV file of data that is read in and then plotted within this map here. And see, this doesn't have really any capability for any interactions, but you can set up interactions to basically on the hover, so that's another mouse event, of certain elements to show data associated with each of those counties. And so there's so many examples, and just going through these myself, sometimes I'll get good ideas for visualizations for meteorological data sets. And with my last couple minutes here, I wanted to leave time for a few more questions, but just some final thoughts. So D3 is not a charting library. So you can get a charting library with, say, Google Charts, something very high level, and if you have some data and you want something fairly simple, that may suit your needs better than D3 can. The barrier to entry is somewhat steep. Hopefully this has given you a taste of what's possible and some of the just high-level overview of selections and the update patterns working with data in D3. But it does take some time to become comfortable with because it's fairly low level. So there's more code than some of the higher level libraries that exists. But it's extremely powerful and fast because of that. And so moving towards sort of visualizing ensemble data sets, it's impossible to visualize every product, come up with static images to look at products, members, forecast hours from ensemble systems. And so part of the motivation here is I think we need more interactive tools to really slice and dice the Ensemble data in the future. And this is one way to do so, to try to learn about these web-based technologies, take some of them, and to really be able to interrogate these Ensemble data sets. And so I'm just going to put up a slide for a reference book that I've found useful. This is Interactive Data Visualization for the Web, an O'Reilly book. I'm designing with D3, and I've found a lot of the examples in there really useful to learning D3 and using web-based visualization technologies. And with that, thank you for your attention, and I'll take a few questions.
I love D3. I'm a huge user, and I think for things like CSV, right, point objects, vector objects, shape files, makes a lot of sense.
Right.
But in order to break into that asynchronous paradigm of visualization, we're going to have to deal with raster data. So, and the only thing that I've been able to use so far is like things like GeoTIFF or tiling
Right.
that make it, useful to use in the browser. So I think addressing that in the future, like being able to read NetCDF and pushing that is a big challenge that we're going to still, otherwise we're going to still be dealing with static PNGs that are just
Right.
KML references in the browser.
Yeah, I've seen some examples with even D3 or Canvas. So Canvas is another web-based JavaScript technology that's actually drawing things in a different way. But I've seen examples where it's plotting and filling contours in the browser. And so, you're sending it presumably large text files, which take up space, and you have to maybe a grid of numbers or something. So it's at least possible, I think, to get to a point where you can take some of that and plot it and apply things like contour plotting and filling to those types of data sets. But yeah, there's a lot of manipulation and massaging of that data that would need to take place before you get to that point. And so there's still a place for some of these basic, just here's some images, having some rollovers. I didn't really talk about some of the design choices for just that alone, which I still think is worth pushing forward, rolling over images. You can do a lot with some very basic web stuff. But I still think there's a place for kind of coming up with these type of visualizations that are sort of simplifying and extracting useful elements of a particular forecast.
Yeah, you had some great examples. I actually have a really simple one online if you have your browser open that uses meteorology data. So the URL is atlas, like a map, .niu.edu/AFD. So atlas.niu.edu/AFD. It's just a very simple D3. Atlas.niu.edu/AFD for area forecast discussions. So it's just an easy way to access the forecast discussions that the National Weather Service puts out.
Right.
And then, so basically the blue lines are just a shape file that is read in by D3 and colored. When you mouse out of an object into an object, it changes colors. And then when you click, it just sends you dynamically to the area forecast discussion. So if you do a Control-U and look at the source code on that, there's really just one file that's the most important. It's map.js. And so you can kind of see the guts, the ins and outs in that. As long as you have so the two important lines there are the CWA.json and the states.json. Those are just converted shape files to JSON format. And then D3 reads them in as objects and plots. So.
Yeah, so all the maps that I was showing use, some JSON files that are plotting, shape files that basically easily plot boundaries on those maps. So this is, this is a good meteorological example of a way to use, add some sort of interactive capability to selecting, say, AFDs. I've seen some really cool visualizations with wind data. Looking at different sites in terms of wind roses that were all basically plotted on maps, and so you could easily go through the site and pick different airports and see wind roses. I've seen other types of meteorological visualizations that make use of D3 that are pretty powerful. So hopefully I'll see more of them going forward.
Thank you. I have one on the same line of the previous question. So in the first examples, you mentioned several examples of visualization that were forecast and so on. What kind of backend you were using in that case? Or just images that were like, I don't know, overlapping some PNG, animated PNG, or there was like an interaction with the data backend, I don't know, MySQL or NetCDF file?
Right, so no databases, it's mostly just static text files for a lot of this. So yeah, here's just, let's see here. Just go to, yeah, these are basically just text files that are read in, CSV files with the data in there. The processing to get to that point, it's mainly Python-based processing that's massaging some of the data that comes out of the WRF out files, takes the data and puts it into CSV format for this purposes, computes some variables, post-processes some of the WRF out arrays. But yeah, really nothing too fancy on the back end. Yeah, just some Python tools and a lot of text files.
So for example, this page, would this be one CSV file that covers all of the stations?
So there's some choices that would need to be made in the best way to organize those types of data sets. So, right, so this is basically just one, all the data is contained for the entire ensemble for all these different fields. So on this page load, it has within memory all the information for all these fields and is plotted for this site for all forecast hours. So it's only requesting a new set of data when you change the station. You go to a different station, then it pulls in a new data set and basically overwrites what data already existed.
So each station would have its own CSV file then,
Right.
and be read. Okay.
Right.
But then, so when you're just changing like the parameter, then you're not actually reading a new data.
Right.
You're just selecting different elements of that CSV.
Yeah, it's sort of a trade-off of having too many text files, and then the size of those files getting large enough where you kind of lose lose the speed of the interaction.
Question over there.
Just because it hasn't been brought up yet, the implications of using this type of technology on the ever-evolving smartphone world is a whole different ballgame.
Right, so none of this has been optimized for mobile. The web browsers, obviously, web browsers are just as modern as laptop browsers. They can run D3 and build these visualizations on the fly. But what you see here is what you get on your phone. So that's obviously a downside to this and a design decision that would need to be made to account for that.
I just want to be on the record saying we want the in-car ensemble back. So make it happen.
Kickstarter? Kickstarter campaign, maybe?
Yeah, Kickstarter.
All right, any other questions for Ryan here as we finish up?
This custom stuff like you're doing with the drawing the wind barbs, is that all, those are just lines, layers, objects, SVGs that you're creating? Can you walk us through how do you create the wind barbs on the fly like that?
Yeah, so the wind barbs are actually, you can create an object and basically store it in D3. So each one of those SVG objects was created initially, just the barb, and then it's really fast to move those around once they're created. So I basically create 5, 10, 15, 20 knot barbs, and it's really fast to just move them or rotate them, right? So you have a barb already, and all we're doing when we're going along this top row and rolling over is just rotating each one of those according to the wind direction. Yeah, so there's lots of little things behind the scenes to make some of these things work, which I'm sure you appreciate. Like this, the storm viewer, there's a lot of objects being created in the browser. And so once you're getting to thousands of SVG elements, it can really slow the, even if you have a pimped out laptop with a ton of RAM, it can really bog down the browser. And so there's some choices that need to be made between if you're drawing them, or if you're drawing them before and then just turning them on and off visually, or drawing them as you're going along. So things like that are kind of challenging, and you just have to go through some trial and error to see with the specific data set that you have what works the best.
All right, great. Thanks, Ryan. Let's thank our speaker one more time.